Hello, so today we will be discussing three topics: derangement, circular permutation, and I guess I don't know exactly. Derangement, circular permutation, and let me just check. Okay, combination of multiset. The three topics that today we are going to discuss. We will be quite fast. It's necessary to sit with a copy. Pause the video whenever you think that you can solve it. So today we'll be discussing three topics: derangement, combination with repetition allowed, and another topic is circular permutation. Circular permutation. Derangement is one of the most important topic, I guess, because this is a new topic and nowadays it's used. So what do I mean by derangement? The basic idea of derangement appeared with this. No. The basic idea of derangement appeared with this, we can say. That we were having to find the number of ways in which a letter can be inserted into a wrong envelope. Suppose we are having 4 letters and 4 envelopes. These are envelopes. Let me name them A, B, C, D. These are the envelopes, and these are envelopes, and these are the letters A, B, C, D, such that the letters will go always to the wrong envelope, and this concept of derangement emerged. Even the formula that is popularly used, that is having its proof using inclusion exclusion principle, but that is not asked in intermediate Olympiad, that how this proof is coming, so we do not need to bother with this. The definition says, in combinatorial mathematics, a derangement is a permutation of the elements of a set such that no element appears in its original position. This is derangement. Now let us move with some illustrations so that it will be quite clear. Oh, before that, the formula. The formula of derangement. This symbol is called subfactorial. And this is the formula for finding the derangement. Suppose we took the example of 4 letters in 4 envelopes. Derangement. That is, none of the 4 letters will go to their original envelope. In such a case, how many possibilities are there? We will denote it by 4 subfactorial, whose value is 4 factorial multiplied by, first of all we'll start from k 0 factorial, then it is just what? It is 1. Then it will be minus 1, because minus 1 whole to the power minus 1 over 1 factorial plus one over 2 factorial up to n minus 1 over 3 factorial plus 1 over 4 factorial. So this is the number of ways. If we just add them up, we will get 4 factorial, these and they'll cancel out. 4 factorial only. 3 4 are 12. Minus 4 plus 1. 4 factorial cancels. Answer is 9. And this is the formula. This is the formula. This symbol is called subfactorial. It will be more clear after we move with some examples. Already we have taken the example of 4 envelopes, 4 letters. There comes the example in how many ways we can put 5 writing into 5 corresponding envelopes so that no writing go to the corresponding envelope. This would be just simply. You can pause it, you can calculate what is the value of 5 subfactorial, because I am not going to calculate the value. I am just telling you the answer. This is 5 subfactorial. Calculation is student's task. Calculation is your task. This is not my task. This is not my task. You can just simply pause it. You can find the value. So those who have paused it and have find out the value, let's check whether your calculation is correct or my one is correct. Five factorial 1 minus 1 plus 1 over 2 factorial minus 1 over. This is the expression. This is the expression. Let us simplify it. This and this will be cancelled. 5 factorial. We are taking the LCM. LCM is definitely 5 factorial. 5 factorial is 120, we know. 2 factorial is 60 minus 20. 3 factorial is 6. 6 into 20 equals to 120. That's why 20. Plus 4 factorial into 5 equals to 5 factorial minus 1. So this will be our result. 60 minus 20, 40 plus 4, 44. I hope that my answer is also correct and your answer is also correct. I don't know what's your answer. I don't know. Yes. Now let's move forward with more examples. 4 slip of paper with numbers 1, 2, 3, 4 are written on them, are put in a box. They are drawn one by one without replacement at random. In how many ways it can happen that the ordinal number of at least one slip coincides with its own number? This is based on application. This is based on application. I want you to solve it. I want you all to solve it. Please solve it. Pause it, solve it. So I am proceeding with the hint. The first hint is that the total number of arrangement total number of arrangement is 4 factorial. 4 factorial. Total number of derangement is subfactorial 4. And this derangement is what? Total number of ways in which ordinal not coincide number of any slip. Ordinal number. This 4 subfactorial, that is the derangement, will give us when ordinal number does not coincide at all. So what we will do? We will just simply the answer, the required number of ways, is simply 4 factorial minus subfactorial of 4. We have calculated already the value of subfactorial of 4. Here you just see that is 9. And 4 factorial is what? 24. 4 into 3 into 2 into 1 minus 9 equals to 24 minus 9. Hence the answer is 15. This was quite easy. In a quiz, two columns of questions. In a quiz, two columns of questions. Two columns are there. Column 1 contains 10 questions and column 2 contains 10 answers written in some arbitrary order. In how many ways a student can answer this question so that exactly 4 of his matching are correct? There are 10 questions and 4 needs to be correct. So we will choose the 4 correct answers. Ten, choose 4. Now there are 6 questions left which cannot be correct, which cannot be in their exact order, which can happen in 10 minus 4 subfactorial, that is derangement of the other answers. So this is 10 choose 4 into subfactorial of 6. This is the answer. Nine students are supposed to sit on an exam. 3 different question set has been created, say A, B, C. There are 3 rows of 3 students each. In each rows, all the 3 sets of questions are to be provided. In how many ways we can provide the set such that no 2 students get the same set sitting opposite? Sitting immediately opposite to each other. Opposite has been written 2 times. Sitting immediately opposite to each other. Nine students are supposed to sit on an exam. This is the sitting arrangement of the 9 students. They are supposed to sit on an exam. 3 different question set has been created, say A, B, C. There are 3 rows of 3 students each. In each rows, all the 3 sets of questions are to be provided. So the first row will get A, B, C. Now the first row, the questions can be arranged in 3 factorial ways. There are 3 rows of 3 students each. In each row, all the 3 sets of questions are to be provided. In how many ways we can provide the set such that no 2 students get the same set? So the arrangement is like that. No one sitting opposite to A will get A, and here also no one can get A. If somebody gets A here, B here, C here and B here, then no one can get A here. A cannot be here. So this kind of arrangements we have to think. So this is typically a question of derangement. This ABC can be deranged in subfactorial of 3 ways. So we will get particular arrangements which again can be deranged in subfactorial of 3 ways. Which will give us the total number of required possible seating arrangement in the examination. 3 factorial is 24, not 24, it is 3 into 2 into 1 equals to 6. Subfactorial 3 is 3 factorial 3 factorial over 1 minus 1 over 1 factorial plus 1 over 2 factorial minus 1 over 3 factorial. 3 minus 1 2, this will be 2, this is also 2. So the answer is 6 into 2 into 2, 2 2 ja 4, 24. This is the final answer. Three couples sit for a photograph in 2 rows of 3 people each, such that no couple is sitting in the same row. No couple is sitting in the same row. Next to each other. If the couples are sitting like that, let the couples be H1 W1, H2 W2, H3 W3. Suppose H1, H2, H3. Then W1 cannot sit here because no couple is sitting in the same row next to each other. Or in the same column, one behind the other. One behind the other, it's not possible. One behind the other is not possible. Or this arrangement also. This arrangement is also not possible. W1 cannot sit here also. So we have to think for certain cases. Possibly the first case can be that all the males are sitting together in a row. H1, H2, H3. Then here will be W1, W2, W3. This is not possible. So this will be, this can be done in 3 factorial ways, and this can be done in subfactorial of 3 ways. Now it is also possible that H1 are here. So the whole thing the rows can be interchanged. So this 3 factorial, subfactorial of 3 we have seen it is 2. This is 6. Will be multiplied by 2. We will get 24. This is the first case. Now the third case, typically the third case, two men, one woman, two men, one woman. First of all, this is the seating arrangement. We will choose two men, 3 choose 2, 3 choose 2. Suppose the arrangement is like H1, H2. Then obviously we cannot select H2. We have to select H3. We cannot select W2. We have to select W3. If we can select W2 here, whether we can or not. Suppose W2 is here. Let's see what happens. W2, then we are left with W3, W1 and H3. H3 should be here or here, either in one of the corners. Suppose in this corner, then W3, W1. This is possible. This is possible. Clearly this is not possible because the H2 and W2 are together. H2 and W2 are together. So the case with W2 was also invalid. Now the case with W1. The case with W1 into consideration. If we consider this case, we are left with W2, W3 and H3. What are the possibilities of placing W2? Either W2 will be placed here or W2 will be placed here, because W2 cannot be exactly opposite to H2. If W2 is placed here, then also W3, H3 are together, and if W3 is placed here, then also W3, H3 are together, which is not possible. So W1, W2 cannot be here. W1 or W2 cannot be here. We are left with the only possibility of W3. So, two men, one woman in the first row. H1, H2, W3, and this is possible. So we are choosing two men. 3 choose 2. We are left with W1, W2, H3. Interestingly, all are distinct. So there again comes the derangement subfactorial of 3. This is 3 into 2, 6. 3 into 2, 6. Now the rows can be interchanged into 2, 12. So maximum 36 we are getting. This H1 and H2 can be arranged in 2 factorial ways, and the rows can be interchanged. H1 and H2 can be arranged in 2 factorial ways. The rows can be interchanged. So this is 6 into 4, 24. 24 up to 24. Now this H1 H2 are here. This H1 H2 can be here also, and W3 here into 2, 48 arrangement we got. Well, let's think it in a little bit different way. Differently. That we will take the case of 2 men, 1 woman. First case we are taking H1, H2, W3. They can be arranged in 3 factorial ways. 3 factorial ways. The possible derangement here, subfactorial of 3. And they can be interchanged among themselves. They can be interchanged among themselves, which give us 2 factorial ways. So ultimately we will get for H1, H2, for H1, H2 only, we will get 3 factorial into subfactorial 3 into 2 factorial, this is 24. Now this was for H1, H2. We were having the whole will be multiplied into 3 choose 2, which is 3 into 24, because we are having 3 such cases, H1, H2. One is H1, H2. Another possibility is H2, H3. Another possibility H3, H1. That's fine. So this will give us, so the total number of cases are 24 plus 3 into 24 equals to 4 into 24 equals to 96, which is the correct answer absolutely. How it happened here, that this H1, H2, H3 can be arranged in 3 factorial ways. this can be arranged in 3 factorial ways. And here the further things can be arranged in subfactorial of 3 ways, which gives us this part. Subfactorial of 3 is 2 and 3 factorial is 6. This is 12. Now this row and this row can be interchanged. This row and this row can be interchanged in 2 factorial ways. This gives us 24. Now this was the case for only H1, H2. We are having H2, H3, a separate case for H2, H3, and another separate case for H3, H1. That is 3 choose 2, which is equals to 3. 3 into 24 gives us the entire thing. Derangement with repetitions. Derangement with repetitions allowed. Find the number of derangement of the world India interestingly, very interestingly, in the word India we can see a special case that I is repeated 2 times. So our formula of subfactorial n equals to n factorial over e will not work. Now how this formula n factorial over e is coming? This was the formula of derangement that we learned. This part approximately, this part when tends to infinity gives us the value of one over e when n tends to infinity. Not like that. So for approximation we can use this, which will give us almost the accurate result. The value of epsilon naught is not epsilon naught, exponential constant. This is very important figure in mathematics. We all know that the number of derangement can be given by this formula also. But now in the word India, there are certain kind of obligations that this is not the true case. So let's find all the number of derangement. There are 5 words. So this will be just simply derangement of 5. Suppose this eyes goes here, then and all the other 4, the remaining 4 are deranged. This eye is going here. This will be an invalid case. We'll subtract it. 4 subfactorial. Now this I can go here and the remaining can be deranged. We'll subtract it. 4 subfactorial. The last case, that this I is here, this I is here. Both of them at the same time are positioned here when they're rearranged or deranged. At that time, only 3 are actually deranged. Subfactorial of 3. This will give us the number of valid cases. But since these I are similar, we will divide the entire expression by 2 factorial. And this will give us the number of derangement. Based on this, the direct question, we will say that rearrangement of the letters of a word has no fixed letters if, when the rearrangement is placed directly below the word, no column has the same letter repeated. For instance, HBRAT is a rearrangement with no fixed letters of Bharat. How many indistinguishable rearrangement with no fixed letter of Bharat do we have? BHARAT. Suppose this A, again, the entire can be rearranged in subfactorial of 3 ways. This A goes here. We will subtract. And the other remaining 5 things are deranged. So this is definitely invalid case. Minus 5 factorial. Now the case that this A goes here, and all the other 5 remaining things, that is this, and this also, are deranged. Again, minus subfactorial of 5, because this is also not correct because one thing is coinciding. The last and the final case, that at the same time this is coming here and this is coming here, this is coming here, this is coming here at the same time, and the others are deranged. So this is also incorrect case. This is also incorrect case. Minus subfactorial of 4. Now this A are same. So the entire expression is divided by 2 factorial. And this is the idea. We need to find the value of subfactorial of 6. We know we have already found out subfactorial of 4. That is value is 9. Subfactorial of 5 also we have found out. Let me check what was the value. This was 44. This was 44. Subfactorial of 6. I'm doing it for fast calculation. 6 factorial is 720. 360. 360 minus 720 divided by 6. 120. This divided by 4 will give us 30. This divided by 5 will give us 6, and this divided by 6 will give us 1. 360, 240, 240 plus 30, 270 minus 5, 265. So this is 265 minus 44 minus 44 minus 9 by 2. This you can find out. Ultimately the answer is this. Ultimately the answer is this. And that is calculation. That is calculation. Let's move forward. Now we'll be coming with redundant combination or combination of multiset. This is really one of the most interesting topics because we have seen permutation with repetition. We have seen derangement with repetition, and we have also now we will see combination with repetition. So this is really interesting because there should not be any kind of partiality. A special note is that derangement, the proof of derangement can be given by inclusion-exclusion principle, which is beyond the scope of our target. The number of combination of n objects taken r at a time with repetition is given by this formula. How this formula is given? Okay, we will approach. The following things are equivalent. The number of combination of n objects taken r at a time with repetition. I guess there should be one example. There should be one example. Number of combination of let us consider an example. In a shop, 3 varieties of fruits are there. In a shop, 3 varieties of fruits are there. How many different combinations of seven fruits can I buy? In a shop, 3 varieties of fruits are there. How many different combinations of fruits can I buy? So based on this formula, we are having n things, 3 different things. And we want to have 7 objects. -1, choose 7. Will give us the exact number of the required combinations. Definitely we will come to the fact that how this formula is working. There is an important thing to note. The number of combinations of n objects taken r at a time with repetition, this thing is equivalent. Let's highlight this also. The number of ways of r identical objects can be distributed among n. You are taking and you are distributing. In the 2 cases you just see. In this case, first of all, I am having 3 things, I am taking r things from them. That is, in this direction this is happening. I am taking r things from them. And in this second case, the direction is just changed. This direction is changed. Now I am giving r things in the n boxes. So they are definitely same. This is also same. The number of non-negative integer solution. Total of r thing. Total of r things. And these integers can be considered as boxes. To be distributed in n boxes. So definitely they are saying this is equivalent to second statement, and second statement is just the vice versa of the first statement. So this 3 statements are equal. If you can prove any of this, we are ultimately proving this. So let's try to prove it. In how many ways can we choose 6 candies from 8 brands that are available? We're having 8 brands, right? Let me choose. Let the brands be B1, B2, B3, B4, B5, B6, B7, B8. These are the brands. We can choose one chocolate or more than one chocolate. That depends on us. Suppose let me choose. Small b denotes chocolate. B1, B1, B3, B3. 6 chocolates here. 6 candies. B5, B6. 1, 2, 3, 4, 5, 6. Okay. So this is my choice. In one hand, this BI indicates brands, and this BI indicates chocolates of the respective brands. So let me consider that this is one of my typical choice. This is one of my typical choice. There can be a lot of such choices, but this is one of my typical choice. Now in between what I have chosen, I have to use some spacers like this. My choices like that. Let me remove it. Suppose I have chosen B1, B2, B2, B3, 1, 2, 3, 4, B6, B8. Then some brands are left empty. In between them, I have to denote empty space. So this is denoting the gap between two brands. These are called spacers. Spacers. B1, B2, B2. Between B2 and B2 there is no gap. B3. Between B3 and B6, how many gaps should be there? B3 and B6, how many gaps should be there? B6, B8. First of all, one gap. Then comes my B4. Oh, this is empty. Then B4 closed. Then comes my B5 here. Then B5 also closed. You just see, here is B4, here is B5. So here is B6 definitely. B6. And B7 is empty. I do not need any more spaces. Now at this point, we can easily say that what we need is just to select these brands Now let me represent the chocolate with some y. This is y, 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 y. So we are just selecting the position of y. So this is what? This is what? 1, 2. How many positions we are having? You just see. 1, 2, 3, 4, 5, 6, 7, 8. Is it correct? How many? What are the total number of spaces we are having? You just see. We are having 1, 2, 3, 4. I'm selecting red. This is appearing blue. Why? Yes, now it's appearing red. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. We're having 13 spaces, right? In between the 13 spaces that we are having totally, we need to select spaces for the y. That is 13, choose 6. Choose 6. So this 13 can be written as n plus r minus 1, and this is r. So we can generalize it. Question directly from INMO. All possible 6-digit number. in each of which the digits occur in non-increasing order from left to right. Example 87750 are written as a sequence in increasing order. Find the 2005th number in this sequence. How we will approach it? The approach is very simple. The first thing to feel is that this is a question of purely combination. Purely combination, because for every set of number there is only one arrangement. There is only one possible arrangement for every set of numbers. All possible 6-digit number in which the digits occur in non-increasing order. So what are the conditions? Other digits less than the last digit. These are the condition or conclusion that we can have. Other digit less than the last digit. Another conclusion, only one arrangement, that is, it's a question of combination. Repetition allowed. So this is purely combination with repetition. This is how we approach the question. This is how we approach the question, that yes, it is a question of combination with repetitions allowed. So what we'll do, we'll just first try to find the numbers that we can make with 1 on the 6th position, and in the other 5th we can have either 0 or 1, which can be repeated 5 times. N equals to 2. This we can do in n plus r minus 1. Choose r. Let's move forward. So as I said, we will begin with 1. We have to create a table. We have to create a table and write down the cumulative sum so that we can approximately come to a point near about 2005. So that's why cumulative sum. As I said, when we begin with 1, the digits in these places must be greater than equals to 1. So what are the options? We are left with 1 and 0. In this way we will proceed. Repetition allowed is 5 because the first only one digit is fixed. So here beginning with 2, digits used in the non-fixed position 2 1 0, n is 3, r is 5. This is 7 choose 5. Now what is the value of 7 choose 5? 7 choose 5 equals to 7 factorial over 5 factorial 2 factorial 21. This is 21. Cumulative sum 27. Beginning with 3. 3, 2, 1, 0. N is 4. R is 5. 8 choose 5. What's the value of 8 choose 5? 8 choose 5. 8 factorial 5 factorial 3 factorial. This will be 42 here. Adding this 9 will get cumulative sum 69. So now beginning with 4, N will be 5 here. R will be always 5. 5. This will be 9 choose 5. So we need to compute this. Compute this. This is your task. This is the chart looks like. This is the chart looks like. I was wrong in this calculation. I accept. So we'll add them up. Cumulative sum. We need to find. Here we will stop after finding 1715. Why this is considered? For reaching at this conclusion, we have to consider that beginning with 8 digits other than the fixed part, we will have 9. R is 5. Using this fact, we can have 13 choose 5, which is equals to 13 factorial over 5 factorial 8 factorial. That you can calculate. I am using the calculator. This is 1287. 1287. So if you just add 1287 with 1715, this will be approximately about 3000 something, which is more than 2005. So at this point we arrive at the conclusion. Then we have to think in this way, that beginning from 800, then let's try with 5, then okay, it's now less, then let's go for this part and this part. Like that we have to reach at the conclusion, and that is where the gist of INMO is. So we'll get the 2002th term as 8633. We have got 8633. Now after that, what are the terms? The terms are 86400, 864100. So this is the 2003, 4, 5. This is our answer. 3, 4, 5. This is our answer. So this was really one of the best questions that can be solved using elementary knowledge of combinatorics. Entering into the last topic, circular permutation. This is circular permutation of 4 objects, but here we are getting only 3 different circular permutation. What is the reason? The reason is very simple. What are geometrical state? Yes, I got it. Whenever we are considering a circle, suppose here is a person, say A, B, another person C, another person D. This arrangement ABCD, another arrangement let us consider. This is not correct. Okay. Now this will be beautiful. A, B, C, D. Here again 4 seats. Now A is here, A is here, B is here, C is here, D is here. In case of a straight line, if we just consider this position as 1, this position 1, this is 2, this position 1, this is 2, this is 3, this is position 4, this is 1, this is 2, this is 3, this is position 4. Now in case of a straight line 1, 2, 3, 4, the arrangements A, B, C, D, and the second arrangement D, A, B, C are different. But in case of a circle, if we just rotate the circle, we will get this arrangement. So by rotation we can get the arrangement. How many times we can rotate and get a new arrangement? We can do this n times. N times rotation is possible. So when in case of a straight line, we are having A, B, C, D. A, B, C, D, A, B, C, D, A, B, C, D. These all are different, but in case of a circle, we can just rotate and find. So the entire arrangement, this is 4 factorial, this will be 4 factorial divided by 4, which will give us, generalizing it, n factorial by n minus 1 factorial. That is the concept of circular permutation. Again and again mathematics is coming. You don't know what is happening. I do not have an idea practically that why it's appearing again. Let it appear. circular permutation is simply n factorial over n, which gives us n minus 1 factorial. Now if, again interesting fact is there, anti-clockwise arrangement and clockwise arrangement are same. Anti-clockwise equals to clockwise, then again the entire will get 2 times of everything, so it will be just divided by 2. This is the case of principle of homogeneity. When anti-clockwise equals to clockwise, we will again divide the thing by 2, because we are getting the same arrangement twice. This anti-clockwise same. This arrangement are considered same. At a dinner party, 6 men and 6 women sit around a round table. In how many ways can they sit if men and women sit alternatively? If we just tag the idea will be stars and bars, or binary sequencing is also correct. Binary sequencing and circular permutation that we are already proceeding. Key idea will be this idea: stars and bars or binary sequencing, whatever is comfortable. So 6 men and 6 women. Let us create the position for 6 men first, then we will think for women. If men and women sit alternatively, this is the case that men and women are sitting alternatively. Green for women, blue for men. This is the only case when men and women are sitting alternatively. So the men can sit in n minus 1 factorial ways. You just see. That is 6 minus 1 factorial ways, and women can sit in between the positions, and these are fixed. This will not get wet rotation, so this is 6 factorial. The answer will be 5 factorial into 6 factorial. This was quite easy for us. In how many ways 4 couple can sit around a round table such that no 2 couple sit adjacently together? This is important. To check that whether, because we're in, this is the last problem, so we're about to end. To check that whether you are understanding. Let's solve it. In how many ways 4 couple can sit around a round table such that no 2 couples sit adjacently together? So first of all, let us consider the couple as one unit. Men 1, women 1, men 2, women 2. Men 3, women 3, men 4, women 4. First of all, in how many ways 4 couples can sit together around a round table such that no 2 couples sit adjacently together? They will not sit adjacently. First of all, there are 8 persons, so we are having 8 minus 1 factorial ways. This is the total number of seating arrangement minus their sitting adjacently together. This we will consider as single unit. This is single unit, we'll consider them, which can arrange themselves in 2 factorial ways, but they are behaving as a single unit, minus 4 minus 1 factorial into 2 factorial, that is 7 factorial minus 3 factorial, 3 factorial into 2 factorial, that you will calculate. This is your task again. We have considered the men and women as a single unit, which themselves can arrange in 2 factorial ways. Now this is the case that they are sitting adjacently. This is the case when they are sitting adjacently. This is the case when they are sitting adjacently. 4 persons, 4 blocks are there who are sitting adjacently with each other in 3 factorial ways. They are arranging among themselves in 2 factorial ways. Five persons wearing badges 1, 2, 3, 4 and 5 are seated on 5 chairs around a circular table. Find the number of ways they can be seated so that no 2 persons whose badges have consecutive numbers are seated next to each other. Consecutive numbers cannot sit next to each other. There was an important thing that I think the question has been altered a little bit. I think the question has been intentionally altered, intentionally changed. Consecutive number 1, 2, 3, 4, 5. Suppose the person with number 1 is sitting here. 2 cannot be seated here. 2 is sitting here. Then 3 cannot be here. Here we can have 4. 3 is here. 5 is here. This is one possible arrangement. Another arrangement. One, two, three, 4, 5. This time 2 is here. Let me consider. Then 3 can be here easily. 5 is here. 4 is here. So the answer is 2. Because if we just rotate this, we'll get arrangement, but these are not different because it's not mentioned in the question. So our answer will be 2. But if they are rotated and it is considered, if it was given in the question like that, the arrangement made by rotating them are different, then we will multiply it. Then we will multiply it by 5. But since it's not given, our answer is 2.